So welcome everybody to this seminar. Today I'm wearing mask because we're in the ICMAB meeting room, and I'm here also with Luis, our speaker. Well, you know that if you have questions, you can ask them using the questions and answer icon here at the Zoom platform. And then Agustin Me, who is the host of this seminar, today he will introduce us the speaker and he will ask the questions that you have in the end of the seminar. I forgot to introduce myself. Well, already you know me. My name is Anna Mai. I'm the Communication and Outreach Officer here at the Institute of Material Science of Barcelona. And I'm very happy to host today's seminar on Plasmonics. So Agustin, the floor is yours. Thank you all for being here. Enjoy the seminar. Thanks, Agustin.
Thank you. So it's my pleasure to introduce you to Luis Pérez. And Luis obtained his PhD at the INFIQC-National University of Córdoba in Argentina with Professor Coronado and Professor Laconi. And his interests are on light matter interaction, nanostructures, synthesis, and electrodynamic simulations. He is currently a Marie Curie Fellow at the NANOPTO group, and his Marie Curie is entitled Plasmonico, Plasmon-resonance driven thermionic emitters for improved solar energy harvesting, with Alejandro Goñi, directed by Alejandro Goñi. And I have the privilege to work with Luis, and I was quite impressed with his skills. He's a chemist by training, but he is also incredible. He's capable of setting up several optical setups. He can perform simulations. And I think this gives him a unique view of the plasmonics field, that he can go in from synthesis of metallic colloids to characterization and simulation. He can have a great overview of the whole process. So I'll be very happy to look what he has to present us today. So Luis.
Thank you. Well, I'm already sharing the screen, yes?
Yes.
Well, as Agustin said, thank you, Agustin. My name is Luis Pérez. I'm working in the NANOPTO group. The topic today will be Plasmonics. And the title of this talk is Plasmon-enhanced light matter interaction from molecular detection to energy harvesting applications. Well, first of all, only one slide to present myself. I'm from Argentina. Argentina is a country that is in the bottom of the world, very, very near to the Antarctica. But we are very far from everywhere, but we have a lot of beautiful things, such as beautiful natural places. If you go to the northwest of Argentina, you will find nice mountains and la Cordillera de los Andes. But if you turn to the east, in the northeast, you will find this, that is the Iguazú Falls, las cataratas del Iguazú, and also a very dense jungle with, well, very nice places. In the south of our country, you can find forests, beautiful mountains, and a lot of lakes. And even more in the south, you will find glaciers. I was planning a joke saying that I would like to break the ice, but unfortunately this is not a joke, because we are losing our glaciers due to the global warming. But, well, I'm not from the south, I'm not from the north, I'm from this province in the center of Argentina that is called Córdoba. Then I will talk about Córdoba, but first of all, I have to tell you that we have our own culture. I don't know if I can move this.
Yes. Minimize it.
We have this kind of dance called tango. Maybe everyone know about this, but we also are very fan of football soccer. But more than for football soccer, we are fan of meat. We eat a lot of meat, but also we have this kind of food for the Italian people. This is called milanesa. That means that it's from Milan, but it's not from Milan. It's called milanesa napolitana. So it's the mixture of the north and the south of Italy. Only there you can eat food like that. Well, I'm from Córdoba, and Córdoba, the natural places in Córdoba are also beautiful, but we have a lot of history. For instance, we have one of the oldest university of Latin America, called the National University of Córdoba, and it's there where I performed my PhD studies under the supervision of Professor Eduardo Coronado and Gabriela Lacón. Well, that's myself and my career, but now let's go to our topic. Nowadays, we have a lot of technological challenges, such as to deal with this increasing energy consumption, but also the demand of information, more specifically this year, where everyone was in their homes. The use of internet and so on increases a lot. And that means that we should still working on have small devices, more smaller devices with more capacity. And in this point, there is a question such as, for example, if the optical fibers made our communication faster, why not to replace this kind of devices that use electrons to devices that use photons? And the answer could be that in the case of light, that is a wave, we are limited by the diffraction limit. So in the case of visible light, the diffraction limit is around, well, in this case it's green, so between 200 and 300. So in this framework, a group of Harry Hadwater, and more specifically Stefan Meyer, proposed this kind of device. They claim that Plasmonic could be a route to nanoscale optical devices. In this case, they are presenting an array, a linear array of nanoparticles that are very close to each other. And they say that perhaps using this kind of system, we can use light avoiding the diffraction limit. This was the year 2001, but at that time there was an increasing interest for nanotechnology. For example, 4 years before this, this group, Catherine Knight, this author, published this article, saying that they were able to detect a single molecule using the Raman scattering, the Raman spectroscopy. In this case, the surface-enhanced Raman spectroscopy. Well, to reach the single molecule level is the highest that one would want. But that wasn't the start of the use of this kind of system. We can go very before in the time, and we reach the 3rd century. And this cap is called the Lycurgus cap. It has this particularity that if the light is shining from inside the cap, the color seems to be red, or it is red. But if you're shining this cap from outside, the color is green. So something is doing this, and something that is also related somehow, with the device that Alberto proposed, and also with the single molecule detection. The thing that all these 3 systems have in common is that they are formed or they have nanoparticles of gold or silver in their components. So I will be very, very proud and happy if I'm able in this talk to explain you these 3 cases. Only with that, I will be very happy. And spoiler, this will be due to the far field optical properties, near field optical properties, and a special case of near field, that is the nanoparticle coupling in the frame of Plasmon. So when we have a metal or a conductor, the free electrons there, we can assume that free electron as electron gas, and the collective excitation of this electron gas is called plasmon. This plasmon has a lot of properties, such as there is a very strong light-matter interaction that's made that in this case we have a very big extinction coefficient, but also scattering and absorption. The near field produced in the close to this structure is highly confined and also enhanced. It can be a strong coupling with molecules or other structures, and during the Plasmon dynamic, it produces hot electrons that can be used for harvest energy or to produce or to catalyze a chemical reaction. And also at the end of the process, all the light that is absorbed start to be only hot. Okay, there are 3 main types of plasmons. The bulk plasmon, surface plasmon, and in this talk I will focus on localized surface plasmon. The localized surface plasmons are present in metal nanoparticles, for instance. The frequency the natural frequency of this plasmon depends on some parameters or some intrinsic features, such as the nanoparticle material, in the case of the electron density and the electron effective mass, but also the morphology and the size of the particles or the structures. That means the charge distribution shape and size. So the simplest case, the easiest way to understand how we get a resonance in this kind of system is to consider a very, very, very small nanosphere that is only around the 5% of the inside of the wavelength. In that case, we are in the quasi-static regime, and the equations are quite simple. We have the extinction coefficients that is like this, and depends on the imaginary part of the polarizability. Sorry. And the polarizability has the shape. Here we have the volume of the element, in this case, the nanosphere, and the dielectric constant of the spheres of the metal, and also from the dielectric constant of the media. So in the previous slide, we said that there are intrinsic features such as the shape, the size, and the material. In this case, we can add the dielectric media. So if we take into account these two equations, we can reach to the resonant condition, that is that the real part of the dielectric constant of the metal should be equal to -2 times the dielectric value of the media. So it will change if we have in vacuum, for example, or air, or if the nanoparticles is in water or in a matrix such as silicon. To take this into account, for example, let's think about molecules. In molecules, the extinction coefficient is mostly the same as the absorption coefficient. Why? Because molecules are very small, and the third contribution, that will be the scattering, is negative. But in the case of nanoparticles, we have to take into account the absorption, but also the scattering, the dispersion of the light due to the nanoparticle. So let's go to the first case that I will try to explain, that is the case of the Lycurgus cap. The Lycurgus cap, when it's shined inside the cap, you can see the red color. If the lights came from outside, you see the green color. This is related to the extinction coefficient and the scattering coefficient. In this case, I have calculated the spectra of silver nanoparticle of 100 nanometers that are inside a silica matrix. That's such in this case. For example, to explain the red color, we should say that if the light is going from inside the cap to the outside, the extinction means that all this light is rather absorbed or scattered. So the only contribution that we are observing is the wavelength that are not totally absorbed. In this case, we are in the red region of the visible spectrum. In this case, it's more or less like in the case of gold nanoparticles, small gold nanoparticles in water, that if you remember, the color is a very red, like ruby color. And the maxima is more or less at the same wavelength, 510 or something like that. On the other hand, if the light is coming from outside the cap, we observe this green color that is due to the scattering of the nanoparticles. If we observe this scattering spectra, we can see that the main contribution to the scattering are around 500 or 500 something. That's are the green region of the spectrum. So that's why we can observe the different colors in this kind of structure. Let's go to the second case that perhaps is more interesting. That is how this group in 96 reached the single molecule detection. When I started my PhD, I thought that single molecule experiments were a very complex one, but you can see that in this case, it will be something very different. For example, let's start to read this paragraph of the article, and let's take notes on this. For example, they are using a Raman microscope and with the laser at 830 nanometers. Why they are using the wavelength in the near infrared? Well, perhaps it's due to they want to measure single molecules, so the signal should be very small, and they are trying to avoid all the background that could be possible. For example, the fluorescence of the analyte molecule, or the fluorescence of other species in the solution. If we take attention to the optics that they are using an objective of very high numerical aperture, and they said that the scattering volume is about 30 picoliters. I have already calculated that, and it's more or less, if we assume like a box or like a sphere, around 30 micrometers in the diameter of the scattering region. So they are only measuring in a very small volume, so that could be the clue of this measurement. To continue, the scatterer and the enhancer of the signal will be a colloidal silver solution. They don't say the concentration, but usually this kind of colloid has a concentration of about these values. That means that in this volume, we will have between 100 and 1,000 nanoparticles. And also they add the analyte. The analyte in this case is crystal violet, and the concentration is quite low. Well, you can see the values. That means that in order to prepare that kind of solution, you have to take micrograms or something of the analyte and then to dissolve in a lot of water, or no, in this case, it was ethanol. They use this concentration because they want to be sure that they will have only this amount of molecules, 0.6 molecule in the scatter volume. That means that there can be two possibilities. If they don't have any signal, perhaps means that there isn't any molecule in the volume. But this is dynamic, so at some point they will start measuring, because they are taking one spectra per second. Then the magic starts when they add a very high concentration of sodium chloride. So let's summarize. They are using a silver colloid solution. They add the analytes in a very low concentration, and they add this salt. So they are increasing the ionic force of the solution. That will make that the colloid will be stable and start to aggregate. And that's the point of this experiment. When the solutions start to aggregate, they will start to have some signals. In our group in Córdoba, we already do things like that. For example, if there are two silver nanoparticles and the distance between them is enough large, you will have something like this. But if you start to put it closer, the spectra will change and it will reach this limit when they are touching. Well, this video should work, but isn't working. So, well, luckily in the next slide, I will explain you why they will start to see some signals when the nanoparticles are very close. At the same time, you are having some changes in the far field spectra. You will have dramatically change in the region intra nanoparticles. That means the hot spots where initially you don't have any enhanced field between the nanoparticles, but at this point and also at this, the field between the nanoparticle, the electric fields, is as high as 70 times the incident field. So 70 times the incident fields is a very enhanced field. If we think that the signal of Raman, of the SAR signal, is proportional to the force power of the field, that means that they are going to have very great enhancement. In our group, we did this kind of aggregation, but using bioconjugation. Instead of using only an analyte, we use this kind of bioconjugated molecules between a protein and an acceptor of the molecule of the protein. Sorry. And also at the moment, in Córdoba, they are still working with this kind of system. Now they are working instead of streptavidin, they are trying to detect the coronavirus in the same protocol. But I will like to explain this branch, where instead of having a protein, we only have two molecules, and the nanoparticles start to aggregate. So it should be like a system like the previous one, like the single molecule system. In our case, the concentration of molecule will be higher. And what we observe is that independently of we were using silver or gold, the nanoparticles start to aggregate. And at some point, you can see this graph and also this, in the case of silver and gold. We will start to have a very strong Raman signal, in this case, SARS signal, but after, well, in this case, 30 minutes or more or less the same time, the signals start to decrease. Why? Should be something related to this dynamic process. You start with a very stable colloid, and these colloids start to aggregate. From the Raman spectra, from the SCR spectra, we can calculate the analytic enhancement factor. and then we will correlate this data with some simulations. We get this kind of enhancement, 10 up to 6. And we develop a model, 2D model, in order to modulate the results. What we found was that if we graph the enhancement in function of the number of spheres, in the case of silver and also gold, we have more or less the same result. The cluster with the highest enhancement are the dimers, or this small cluster. When you start to have very large cluster, the enhancement is more or less always the same. So that's the message, that if you want to have a very large enhancement factor, you should find the condition where you aggregate your colloids, but not to have very large cluster, only to have a cluster of 3, 4, or something like that in the number of nanoparticles. Well, we rationalize these results, making a lot of calculation and taking into account the enhancement, in which place of the cluster is the best place to enhance the signal of the molecules. And we found that in the case of very big cluster, only this region was a very good enhancer. Then all the hot spot in the middle of the cluster were not enhancing because the electric field was very low. Well, we try to emulate the natural vacancies that are originated during the aggregation process. And in that way, we reach to something close to the analytic enhancement factor. But let's continue with this. In this case, we have well, we can say that this is a cluster, but a very ordered one and linear. And I did some calculation, not for this, but it can be useful. For example, when you have a linear cluster, you will have that the electric field is located in the hot spot. So that's go very good with the idea of Mayer that it was to illuminate in some region of this cluster. And due to the nanoparticle coupling, the energy or the light, the near field, will be transferred to the other side. But to be success in this kind of system, we should be sure that the light wouldn't be absorbed. So it should be find the solution to have a non-absorbed structure in this case. There are a lot of groups working in these topics, and they are trying with different kind of materials. But well, when you are calculating near field, you always get this kind of distribution. And for me, it was very important to see in some experiments this kind of distribution. But unfortunately, there in Córdoba, we didn't have the instrument that we require. But there are some equipment measured directly somehow the near field distribution. I said somehow because instead of using light to excite the nanostructure, they use electrons in equipment similar to a scanning scanning TEM, you can take not only the electron energy loss spectroscopy, but also the light produced by the nanostructure. In this case, the cathodoluminescence. Sorry if there is one mistake here. How you can get to that? Well, here you have the electron gun. You, as usual, you have the sample here. And when these electrons interact with the sample, it can excite some plasmonic modes. So a fraction of that energy is used to excite the plasmonic modes of the sample. So then this electron continue. And if you have a spectrometer that in this case are a magnetic lens, you can separate the contribution and to know the energy loss of each electron. So in that way, you can get this kind of spectra when you know exactly the energy that you're losing that is used to excite the plasmonic mode of your sample. But also, as a counterpart of this, when you are exciting a mode, that mode can be radiative. So the energy that comes from the electron can be radiated into photons that can be collected here in a CCD. Well, it's similar to a conventional CCD. And you can also take the image of the cathodoluminescence. So in this case, you are measuring photons. There are some other approaches in order to be able to measure the near field directly, and are using Proob's microscopies. I will show you two kinds of this microscopy with some examples: the TER's spectroscopy and the Nson microscopy. In the case of Nson, Professor Goñi, a couple of years ago, we did some experiments using the Nson that we have in the group. And the system in that case was zinc oxide nanowires. So they did a very good work, and they get this beautiful image of the whispering gather modes of the single nanowires. Here you can see the topography of the samples. And using two different wavelengths, you can see in two, well, these are two nanowires with different diameters. And you can see the near field distribution in this system. After that, we performed some calculation, and happily we found that we were able to modulate the experiments in a very good way. And the other thing that I want to show you is a case when using TERs, we can analyze the system of gold nanoparticles on top of CVD graphene. In this case, this was the graphene was transferred into a glass or silicon substrate with, well, or using gold nanoparticles. We got a distribution of nanoparticles, in this case, hexagonal and triangular ones, and also small nanoparticles. When we work with the big nanoparticles, and we perform single nanoparticle, or in this case, microparticle spectroscopy, We took the scattering spectra and also the correlation between the AFM and Raman imaging, or in this case, SCR's imaging. And it was very funny because I was very interested on measuring the optical properties, and I forget why was the reason that we get this kind of very big nanoparticles. There were some other people smarter than us that published 2 years after we published this article, analyzing how it's possible to get this kind of particle in the system of gold particles or gold and CVD graphene. But the focus of this article was to measure this, the tip, hence from spectroscopy of the system. And at that point, I start to know that when I make contact with the tip, the tip is a conventional AFM tip with a gold nanoparticle on the tip of the probe. So when this tip interacts with the system, I start to see that there were a lot of changes in the optical properties, in the spectral properties of the system. For example, you know that in graphene, you have 3 main bands, Raman bands, the D, the G, and the 2D. And all the bands change, but in a reversive way. So I start to like going and touch the sample with the tip and going up, touch the sample, and I observe that I can make this kind of plot where I always have the same kind of response. In this case, we analyze the spectroscopic features of the sample, and we get that when the tip was touching the sample, we get a higher intensity of the 2D and a lot of small features here that could be due to the enhancement of the gold nanoparticle to the sample, but also, as in this case, to the deformation of the graphene due to the pressure applied by the TR's tip. Well, after years and years of research around the world, there are lots of groups that are specialized on plasmonic. And 2 years ago, they wrote a roadmap where each of the most important groups of the world, they said, well, according to them, the important things to continue working in this field. I have put in some groups. For example, all that I have shown is regards to this group, the nanoscopies and spectroscopies, but there are other kind of systems to work to do, such as to find alternative materials to gold or silver, to noble metals. And there are groups working on chalcogenide superconductors, and those semiconductors. And also in the direct applications such as biology, energy harvesting, and so on. And well, in this case, I didn't know how to characterize this, so I put quantum plasmonic. That is this case when they are interested in very small spaces in between the nanoparticles. And also, if you have this kind of autolasers, you can do this kind of dynamics. In the last year, there is an increasing interest in these 2 steps of the plasmon excitation. No, you start here, you excite the plasmon, but at some point, this plasmonic, the coherent motion of the electrons start to quench, well, it has this kind of damping. And in these two steps, before the total thermionization of the system, you can use the hot electrons to produce a chemical reaction, or to try to harvest that energy in some kind of solar cells. For example, in our project, Plasmionico, we are working in this kind of system. We have a silicon substrate, some gold nanostructure on top of the silicon. What we want is to use these hot electrons in this very simplified 3 steps procedure. To generate the hot electrons, the hot electron should go to the interface between the metal and the semiconductor, and finally should enter into the semiconductor. In that way, you are using the energy that is accumulating in that hot electrons to produce currents, to use that for energy. So our goal should is to produce a cold cathode in order to harvest the infrared part of the solar cell, of the solar spectrum, sorry, because we are working with silicon substrate, so the visible range is used, but the infrared, the silicon is transparent to the infrared. We have a very determined work frame that is using calculation. We can find the optimum architecture to do in the laboratory. Then, using a combination of chemical and physical procedure, we get the structures, and then we correlate the expected spectra with the calculating one, and finally, that is the more challenging step, to extract some current from that kind of structure. We have already a lot of very nice structures, and we also have a very good correlation between the optical properties of the structure with covered with gold. So now we are in the last step, and more challenging, and I should say that is to get some current from this kind of structure. I have to thanks to Jinhui, that is Jinhui, Isabel Alonso, Miquel Garriga, Juan Luis García Pomar, Agustín Min, Professor Alejandro Goñi, and Sebastián Reparaz, because, well, when I arrived to Spain, and during the time that I have been working here in ICMAB, they have been very kind and very good to work with them. Okay.
Okay.
Thank you so much. Thank you so much, Luis. Very nice presentation. So, are there any questions from the audience? Okay, I could start by. So, could you give us an overview of the SERS field? You know, plasmonics have been used for SERS sensing, and you have shown the work where they detected single molecule. So is single molecule, first, what's the status nowadays? And is it single molecule detection being the standard in the field?
No, I think that a single molecule was the challenge of that years. Every group of the leading groups want to have this kind of single molecule spectrum. But nowadays, they are more focused on having a more robust cells substrates. That means to have perhaps a less enhancement, but if you are in different position of the sample, to have more or less the same signal. There are lots of combination between cells and other techniques such as electrochemistry. Some groups are working with are following the electrochemical reaction using cells and also the catalytic reaction using cells. There are a lot of to do, even though the last 2 decades have been devoted to the study of this kind of systems.
Mm-hmm. And regarding this hot electron system, can you tell us a little bit about the efficiency that you can expect? How much can you improve or...
Well, the efficiency we want to have as high as possible, but there are a lot of discrepancies in the literature because well, it's very difficult to know when you are measuring your hot electrons and when you are measuring some other things. So I don't have a clear view up to now about which is the efficiency that we can get.
From the, someone wants to ask something, just write it in the chat and I can ask as well. And okay, so I'll ask you one more for my interest, my personal interests. So how can we use plasmonics for light emission? Because this has always been, it's kind of challenging given the absorption of the metal. Mm-hmm. So what are the keys? What will be the recipe to do that, to show enhanced emission with plasmonics?
Well, we should find the combination of parameters that allow us to get a very enhanced near field, but also with not too much losses. And it's very challenging. That's why people try to do, well, this kind of array in such a way to have an extra light scattering in order to get the light emission.
So we have questions from the audience. So Mariano is asking, what is the theoretical efficiency of the hot electron approach for energy harvesting?
That's I
yes.
mentioned up to now, I don't have a clear view of that. I hope so in the next month I will have.
And Juan Luis is asking regarding the aggregation systems, how affects that the distance is 8 nanometers when they aggregate for this COVID? This is not too much distance between the particles?
No, in the case of COVID, I think that now they are working with a distance of, well, between 50 and 100 nanometers, because they are not using the near field, they are using the depletion of the far field spectra of the nanoparticles. There is a kind of technique called, well, I didn't remember this time, IDILA, where they describe how you can note that you have the analyte without the near field, only looking at the changes in the excision spectra, but not shifting not shift in the maximum, only increases or decreases of the intensity.
Okay,
you can look only for Eduardo Coronado, and I think they are now working on that field.
Camila is asking, regarding the COVID detection, how does it work? What is the molecular target they detect and how they isolate it from blood or saliva, for instance?
I don't have too much information about that. I know that they do always the same. They add to both biotinylated antigen or antibody, and then the bioconjugation is automatically. But I don't have the details about the procedure. One more, you can look for IDILA, is the name of the technique. IDILA Eduardo Coronado, and you will find it.